Greetings and welcome. We're talking about page 620, analytic geometry homework right here. Here's problem 21, which is actually going to have to call back to some of our algebra skills, possibly even solving a quadratic. I'm interested to see what happens here based on my predictions. So it says find all values of A so that the distance between the points A, comma, -9 and negative 2a plus 7 is 20 units. So they're saying the distance is 20 units. So this is one of the classic, it's a classic math problem here where I know a formula, I'm going to plug in what I know and solve for what I don't. It's a real classic setup. You can actually do it for pretty much any formula that happens in mathematics. They'll usually have some problem like this at some point, right? Like you'll have y equals mx plus b, and instead of knowing m and b, I'll give you a point for x and y, and I'll give you the slope, and then you have to find b, right? Plug in what you know, solve for what you don't. So let's actually plug stuff in. Actually, in my case, I'm going to bring the d over to the right-hand side. So I'll have the square root, roast square root there, of, well, let's label my points here, why not? Why not we? X1, Y1, X2, Y2, just so I make sure I plug them all in the right slots. So I'll have X2 is negative 2a minus X1 is a, all squared. This problem just simplified a lot more than I'd hoped it would, but that's okay. It's still a great problem. I was hoping to have to like solve for real quadratics. This will be kind of an okay quadratic. Y2 is 7 and Y1 is negative 9, so minus a negative 9 here. Careful with the double negative. And I'm saying that that is going to equal to 20, right? So let's start simplifying this. Negative 2a minus a is negative 3a. All right. 7 minus negative 9 is 7 plus 9, so that's 16. Ooh. And the square root equals 20. Now, I'm going to actually want to get rid of this square root. How could I get rid of this square root here? Oh, I see your temptation to do that. That would actually be super illegal only because you can't distribute a square root over addition. But I do see the huge temptation there. Square roots and squares definitely would be a temptation. So what's another way I could get rid of that square root? Maybe I'll come back to that in the next step. Yeah, square both square. Oh, yeah. Yeah, that's exactly what we'll end up doing in a second. So let's see, negative 3a all squared, that's going to be 9a squared, plus, let's see, 16 squared. Oh, man. I don't remember what that one is. Is that 256? What is it going to be? 256, yeah. Equals 20. And now to get rid of this square root, because I can't solve for anything from this point, right? I can't subtract 256 from both sides until I get it out from underneath this, you know, terrible empire of the radical that is ruling over it right now. And the way I could get rid of that square root is to square both sides, as we said a moment ago. So I'll have 9a squared plus 256 equals 20 squared is 400. Right there. And now I can start solving this. Now, I do want to point out this is a quadratic, but notice that there's no b term. There's no like a to the first term. So I actually won't have to solve this by factoring. If that was the case, I would have set it equal to 0 by subtracting 400 from both sides. But because there's actually only one variable kind of represented here, there's one expression of it, I guess, I'm just going to isolate that, and I think I can solve this, you know, without too much challenge. So I'm going to subtract 256 from both sides. I'll have 9a squared equals, let's see, 400 minus 200 is 200 minus 56. So, oh, 144. Wow, interesting. Oh, I see where this is going. Now what would you want to do next to get a by itself? You actually could, because 9 happens to be a perfect square. Normally I would save that for last. I'd get rid of the 9 first. So I'm going to divide by 9. But you wouldn't have been wrong for root rooting. It would have worked out pretty well in this case without making any ugly radicals or anything. 144 divided by 9 happens to be a perfect square. I think it's 36. No? 16? 16, sorry. Yeah. Yeah, because, 3 times 4, 3 times 12, 12 times, yeah. And now I'll do the root both sides. However, when I root both sides, I get a plus or minus. Don't forget it, right? Because there's going to be 2 possible answers to this equation. And I'll get a equals plus or minus square root of 16 is 4. So that means you could actually write it as a equals 4 or negative 4 if you wanted, but that's what plus or minus essentially means. So there's 2 answers here. That means I could have actually plugged in 4 for both of these, and I would have had 4 comma negative 9 and negative 8 comma. Why did I write a plus 7? That's weird. That's a comma there.
Yeah, I did in the very beginning.
Oh, and I didn't notice? I'm sorry. I was just like on a roll apparently. But yeah, so you could plug in positive 4s and it would work, or you could plug in negative 4s. And negative 4, negative 9, and positive 8, 7 would also work. So, excellent. I like that problem a lot. Let's see, problem 23, I guess I would have to give the instructions on this. This problem was, let's see, this problem was specifically about determining whether those 4 points make a, not just a quadrilateral, but a parallelogram. So let me actually start by plotting. Let's see, plot points. I'm going to plot these points, negative 2 and 3. Bam, there's one. Negative 3, negative 2. Then I'll have 2, negative 3, and I'll have 3, 2. So I'm just plotting those points real quick just to get a nice little shape. I'm going to hide these guys. Not that one. And I'm going to scale this up. And in fact, I might even, can I construct segments? Nice, look at that. Wow, that almost even looks like a square. It's so cool. So let me grab a nice snapshot of this. So you would have, I definitely recommend drawing a little sketch for this first of all. Primarily for the purposes of labeling, it doesn't actually have to be super accurate. So let's see, negative 2, 3 is this point here. I'll label this point A. Let's see, let's see, they labeled negative 3, negative 2. So here's B. It looks like they went counterclockwise here. That's fine. Over 2, negative 3. So C and D. There we go. So those are my 4 points. And now I want to figure out, is this, in fact, a quadrilateral? Now we have 4 techniques that we could use to do this. One of them, can you guys name one of them? Midpoint what? Midpoint A, C, and B, D, and finding those midpoints would do what? What do I want them to be? I'd want them to be the same, and what I would be doing is showing that the diagonals of this figure bisect each other. So if I could show that this length and this length are equal, and this length and this length are equal. They don't have to actually be equal to each other. Unless it's a square, they will be. But that would prove that it's a parallelogram. That's one way. Another way, I could prove that opposite segments are congruent. So both pairs of opposite segments are opposite sides. I could show that both pairs of opposite sides are parallel. I would do that using the slope formula. I could show that, let's see, I could show that one pair of opposite sides is both congruent and parallel, and that would also do it. So we've actually got at least 4 ways to do this problem. I might do, I think I might do the congruent parallel one just to demonstrate use of the distance formula and slope formula side by side. For the sake of this example, the easiest way though is midpoint formula. You just do 2 midpoints of the diagonals and you are awesome. So that's the easiest way. So let's see, let me first try to prove that AD is the same length as BC. So to find AD, length of that segment. I'm going to plug it into the distance formula. So A was, let's see, I guess I should label these a little bit. So this is my A, B, C, D. So let's see, for the case of this formula, this will be x1, y1, and this is x2, y2, right? Okay. So let's plug them in. So I'll have 2 minus 3 all squared plus 3 minus a negative 2 all squared. So that would equal negative 1 squared plus 5 squared. So that's going to be positive 1 plus 25. I'll get the square root of 26, which I think is irreducible because 4 doesn't go into it, and 9 doesn't go into it, and 16 doesn't go into it. So there's the square root of 26. So let's now find the length of BC, and hopefully these are the same is my goal here. So BC, I'll have the square root of negative 3, nope, let's see, 2 minus negative 3. Definitely has the potential for dyslexia here, mixing up these numbers. Plus, and let's see now the y's, negative 3 minus a negative 2. And there we go, it's good enough. So that's the square root of 2 minus a negative 3 is plus 3, so that's 5 squared. Plus negative 3 plus 2 is going to be negative 1 squared, and I think I can see that this is going to be equivalent. So that's the square root of 25 plus 1, square root of 26. So, therefore, I have just shown that, let's see, I just proved that AD, the segment, is equal to BC. All right, they are, in fact, congruent there. So these are, that's what I've just proven. Now to prove that they're parallel, what good does the slope formula do for me? What do I want the slope formula to tell me? Same slope, because if lines have the same slope, they are parallel. So the slope formula, so I'll find the slope of AD, slope formula y2 minus y1, so 2 minus 3 over x2 minus x1, so 3 minus negative 2. There we go. 2 minus 3 is negative 1 fifth. So there's the slope of AD. Let's find the slope of BC. And that will be, let's see, it'll be this guy right here, negative 2. No, negative 3 minus negative 2, I believe, over 2 minus negative 3. And I'll get, that's negative 1 up top and plus 5 on the bottom. So I've just shown that the slopes are the same. Therefore, I have proven that AD is parallel to BC. Okay? And by proving both of those things, I have just shown that quadrilateral ABDC, nope, ABCD is a parallelogram. Yay. So the proof is in the work that you show, it's not in the conclusion. Because I just as easily could have come to the conclusion that no, it isn't a parallelogram because the distances were not the same, or the slopes were not the same, or if I did the midpoint of the diagonals, that those were not the same. So the actual proof was the answer, not the conclusion that you came to. But so there's a bunch of different ways you could have done this problem, but this way at least demonstrated some distance formula and some slope formula, making sure we're awesome. All right, internet friends, thank you for watching. Bye-bye.